So I have a question from lecture 4.
Mm-hmm.
So in the energy balance equation, you have said that for laminar flow, the average kinetic energy is U square, and for turbulent, it's half U square. But for
Mm-hmm.
laminar flow, if I calculate the kinetic energy, it turns out to be like V max square divided by 6. If I integrate, so how U square there?
So I will need to, and what is the relationship between V max and U average?
Well, then V max is equal to twice of V average.
V max is twice of average. Okay. So, and you're saying you're getting V max square divided by 6.
Yes.
Okay, I will need to check. Okay, so the answer I gave it was in terms of U average, not V
Hmm.
max. But given what you are saying, I must be getting 2 by 3, you are saying, not
Hmm.
U square, right? Anyone else has calculated that?
Also, I'm using like that formula for cylindrical pipe. Like,
No, that is okay. That's what you need to use. Let's just see what you have done. I believe this is on page 3. All right. So this is the approach you have followed. I want in laminar flow, kinetic energy per unit mass. So for that, I take a cross-sectional area at R, and its width is delta R or dr, and that's either way you can work. Okay, and here the velocity is, let's say, ur. So that is the R dependent velocity. So now in this shell, kinetic energy per unit mass would be equal to 1/2 u square. Now, did you multiply this by mass? You have to first get kinetic energy in this shell as 1/2 u square times the mass flow rate. So did you do this also? Because the mass in different shells would be different.
oh, okay. No, sir, I missed this point.
Okay, so try this and then recalculate.
Okay, okay, sir.
Okay, because you should not be averaging 1/2 u square. So overall, what you need to find out is for the entire cylinder, right? So you're taking a cylinder, right? Like the way it is shown here, right, on the left. So
Yes, sir.
in this cylinder, what is the total kinetic energy? Also for the cross section. So you want for the cross section, what is the kinetic energy per unit mass? Therefore, averaging this quantity would be wrong. All right. So
Yes, sir. Yeah, I understood.
rather, you want in the numerator kinetic energy across the entire cross section, in the denominator mass flow across the entire cross section. Okay. So mathematically, what that means you have to calculate is to get this kinetic energy per unit mass, integral of 1/2 into m naught to u square, um, 2 pi r dr, right? That would be the cross sectional area divided by m naught 2 pi r dr. Okay, that is the integral you want to calculate.
Okay, sir.
Okay, so try that out and see if you indeed are getting 1/2 u square on doing that. Oh, sorry, u square, not 1 half u square, u square. Okay. Anything else? Other questions? So I highly advise that please start asking questions. I should not compare across batches, but I will show you what all was happening in the previous classes. In some of these lectures, you will see a lot of stuff on this right hand side. Okay, and all of this stuff on right hand side was because someone asked a question. So this is the material from the previous year, and you can see on everything on the right hand side, all the discussion is because someone asked a question. So unless and until you ask question, I have uploaded the lecture. So I would not know what point was understood, what point was not maybe understood as well, and requires more discussion at the student end. And if you have gone through the lectures, I will be surprised you don't have questions. If I go through that material again, I will have questions. So if you have gone through that material, there are questions which are marked for discussion within the lecture material. Ask those, but you have to pinpoint that this is the question which was asked or marked as question for discussion. Can we please discuss? So unless and until it is coming from your side, I have uploaded the lecture. I don't need these discussion sessions. Okay. So last call for questions. Otherwise, I will just go on to solving a couple of tutorial problems.
So,
Yes.
in the lecture on PVT, before the N2 cylinder, nitrogen cylinder wala page, can you open that?
Can you also tell me page number? That will help.
Just should be page 3, I guess.
Mm-hmm.
So, not, so
Page number will be marked at the top.
when we were discussing the transformation from D to E, the previous graph in the PT curve,
Transformation from
D to E in the PT curve,
on. Okay.
the DIY
Mm-hmm.
questions. सर PD लेस देन PC होगा या PE लेस देन PC होगा?
No, but we're talking about isobaric, right? So D to E is an isobaric path. So you are right. Yes, that
Okay, okay.
I need to focus on E because I'm talking about what is happening from E. But D to E is an isobaric process.
Okay. So, also, what is the use of this temperature bath? Like just for temperature constants, right?
Yes, and actually, if you go to a laboratory, right? Many times, if you want to use a or you want to carry out a constant temperature process, because for example, temperature will affect reaction kinetics. So you use the temperature bath, and one easiest temperature bath. Maybe you can tell what is the easiest temperature bath which you can have in a laboratory.
Something submerged in water maintained at some temperature, I guess.
Yes, so many times that is the default option. Okay, if let's say I want temperatures above 100 degrees Celsius, I will use steam. If I want temperatures below 100 degrees Celsius, I will use cold or hot water. Okay, and I will just maintain the temperature of that water, and I will just circulate that water around a vessel where my process is happening to maintain the temperature of the contents within the vessel. So this temperature bath is showing that only, that I have some means of maintaining the temperature of the system. Okay, questions I would have asked, for example, okay, somewhere here I believe I mentioned water's phase behavior is quite different. Can anyone tell me how? So this point is mentioned here. Water structure is determined by hydrogen bonds. It has a very different equation of state compared to similar molecules with respect with molecular weight fluids. So compared to other molecular weight fluids. Okay, let's say ammonia. So if I compare ammonia and water, you will see it's not that much of a molecular weight difference. But phase behavior is very, very different. So in what ways it is different? And can you relate the macroscopic information? The macroscopic information is phase behavior, equation of state, phase diagram. Can you relate that macroscopic information to microscopic information? Microscopic information here is the nature of interaction. So anyways, because the questions are not coming right now, from my side, I will not discuss these. So you have one more chance in tomorrow's tutorial. So think about those questions, go through the material, and then put those questions for discussion. Okay. Any other questions?
So I have another question.
Mm-hmm.
For open system or like a flow kind of system, when we are doing the energy balance, why aren't we taking the convection terms?
Okay, let's go there. Which convection term you are referring to?
Like in transport phenomena course when we studied, the energy balance equations are pretty long. I mean, there are a convection term due to the flow of the bulk of the fluid, and also a conduction term, but we can neglect the conduction because maybe that's negligible. But as the bulk of the fluid is flowing with some velocity, then the entire energy will also flow. So can't we consider that term in the energy balance?
But we are right. So if you go to the, let's see, okay, let's take one more step back. So the net energy transport by flow streams is the convective in and convective out. And that we are further saying is composed of three contributions. The flow stream has its internal energy. Further, because of its velocity, flow stream has a kinetic energy. And depending on where it is entering the system, it can have a potential energy component also. So U plus half U square plus Z times G gives me the total energy of the flow stream per unit mass, joules per kg. I multiply that by the mass flow rate, which is kg per second. Multiply that by joules per kg, I get joules per second. That is the rate of energy transport by the flow streams, which basically means because of convection. Does that answer the
Yes,
question, or
yes,
are
I
you?
get it.
Huh?
Yeah, yes, sir, I get it. I
Okay.
missed that point.
Okay.
So another question, in the work done calculation, uh, by the flow work, we have
Mhm.
calculated work done equal to like P minus P delta V and then minus PV. So what is V here?
P is the pressure of the flow stream. So the way we are visualizing this is that a packet of fluid entering the reaction vessel or the system, or actually here the correct word would be control volume. So a packet of fluid is entering your control volume. That packet is being pushed by a pressure P into the control volume. So that P is the pressure of the flow stream, therefore, because there is nothing else. Okay, a flow stream is entering a reaction vessel because of its own, but that because of its own is because of its pressure. If the pressure of the flow stream is less than the pressure of the vessel, it will not be able to enter. There will be backflow, right? So that
Yes.
P is indicating the pressure of the flow stream.
And so we should be taking like the total control volume, right?
No, no, no. V is the volume of this packet which is getting pushed in.
Okay, okay, okay.
Because
Yeah, yes.
the control volume has whatever volume it has. But now by putting that additional packet of some volume V into the control volume, you are in effect compressing the control volume. So that is the visualization here. Okay, that if you want to put that packet inside control volume, compress the existing contents of the control volume. Okay, so that delta V here, if is the change in volume, V I have put as equal to minus V. Okay, the control volume has compressed to allow a packet of volume V. So here I fix the mass. Let's say the mass was 1 kg, specific volume is V. Okay, or if we are talking in terms of moles, so here I have multiplied everything by m naught. If I was multiplying everything by n naught, then I would say I am using molar volume. Okay, so then I'm saying if I want to put 1 mole of my substance inside the control volume, its molar volume is V. That means the change in volume of the control volume. So delta V is a change in volume in the control volume, would be equal to molar volume. We are taking here as minus because volume needs to compress. The contents of the control volume need to compress. So that additional packet of fluid can be put inside the control volume.
Yes, I get it.
Okay, so unit mass volume was V, and therefore work done minus P delta V became equal to PV.
Oh, sir. Sir, in this general energy balance equation, the units of enthalpy are joules per kg, right?
I mean, depends where I am referring.
I mean, joules per kg or joules per mole.
Yes,
Any.
yes.
And what are the units of W naught? I mean, the other work. Is it joules per kg or it is only joules? Because
So
according to the consistency, it should be only joules, right?
yeah, so see, it depends on how you are defining everything here, right? So if I look at here, right, equation 2.9. So equation 2.9, each term together, right? So I'm taking everything in that term. What are the
Yes.
units? So let's take a look at that first. Each term individually. So that means this entire thing together. Similarly, this entire thing together. What are the units?
So joules per second.
Joules per second. So I think you have your answer now, right?
Yes,
So
sir.
that means this W naught has units.
Joules per second.
Similarly, Q naught.
Yes. Thank you, sir.
Okay, but it will W and Q, we are not putting a superscript T. So it will depend on the context. That means the way you are writing your equation, W naught might be joules per second, or it might be referring to joules per mole per second, joules per kg per second. So that just depends on how you are defining all the other quantities in your equation.
Yes, sir.
Other questions?
So in the control volume discussion we were just having, the pressure was just the static pressure, or we were also considering the motion of fluid?
No, P is the static pressure.
Mm.
But again, that P would be affected by like we call the Bernoulli equation. Here we ignore friction, and I take 2 points in a flow system. The pressure and velocities are related at those 2 points. So along a streamline, pressure and velocities will be related to each other by the Bernoulli equation if you ignore the friction effects. That means fluid viscosity, okay, in pipe flow. But yeah, P here is static pressure, but it will depend on the velocity indirectly. Does that make sense?
Yeah, yes.
Okay, so they are still interrelated quantities because of energy balances, mass balances.
So can you explain how in the PT curve, I mean, even if the volume is changing, the PT curve is same and vice versa for PV curves? Uh, I mean, equation by equation, it shouldn't, I understand, but what is the physical essence of that?
So the main physical reason is that at coexistence, I have a single pure fluid. That's what entire chapter 3 is all about. So for a pure fluid, when it is at coexistence, it means the pressure and temperature of the two phases. So when it's a two coexistence, let's say I'm talking about liquid vapor coexistence. So the pressure and temperature of the two phases are the same. That is a requirement of equilibrium. Okay. Now that means that is the easy part. That is just the requirement of equilibrium, that P and T need to be same. So in that sense, the difficult part becomes that why the V is changing. So I'm kind of inverting your question. Okay, so I'm first explaining why P and T are same, because that is a requirement of equilibrium, that at equilibrium, and we will actually show it, okay, as we go along. So when you have two phase coexistence, both the phases need to be at same pressure and same temperature. That is the requirement of equilibrium. Okay. So now the question comes, why this, the way we are defining our V, why this V is different? So can you take a crack at that? Why this V is different? Refer to Gibbs phase rule. Those intensive variables are related to what? To what?
So different phase compositions. Yes.
No. The intensive variables that are entering the Gibbs phase rule. So Gibbs phase rule is applicable to a set of intensive variables, right? It tells you how many intensive variables you need to fix so that all other intensive variables take a unique value, right? That's what the Gibbs phase rule tells you. But it is applicable to a specific set of intensive variables. So those intensive variables are what? Homogeneous phase or properties of system?
Properties in this case, right?
No, but properties of what? Properties of system or properties of a single homogeneous phase?
Oh, mm,
Single homogeneous phase, sir.
Single homogeneous phase. So I'm making this drawing again of coexistence. Let's say I have vapor liquid coexistence. And let us say the fluid is H2O at 1 bar and 100 degrees Celsius. Okay. So I know by experience density of steam is not same as density of liquid water. Okay, steam is nothing but vapor, H2O, right? So these two densities are not same. You can invert that. So at this point, at coexistence, I know that these two volumes will not be same. Specific volume of the vapor will not be the same as specific volume of the liquid. Okay, however, if you look at equation 3.1, and because I have H2O, single fluid, so what is the F value? For this species at coexistence, what is F? Or let's say two options. If you had a pure liquid or pure vapor versus your coexistence, so what will be the value of F in two cases? Pi equal to 1, what is the value of F? Degrees of freedom?
2.
Okay, and when pi is equal to 2, it will become 1. Okay, and here that means I said I have coexistence. I just need to tell you one of these two. That's why I told you pressure. Temperature would not have been an independent quantity because degree of freedom is only 1. If I tell you 1 bar, you would tell me the temperature is 100 degrees Celsius. Okay, and if it was only one phase, then I will need to tell you both P and T. Okay, now let us come to the last point, which is what are my Gibbs phase variables? So VL sat, which is the volume of saturated liquid. Because I'm specifying I have saturated liquid, I don't even need P and T, I only need to specify one. So I'm specifying, let's say, the value of pressure. So VL sat and VV sat are Gibbs phase variables because these are properties of a single homogeneous phase individually. Okay, so VL sat is property of saturated liquid pressure, and VV sat is property of saturated vapor at a given pressure of that pure species. In this case, the pure species is H2. So this implies these two quantities are fixed once I specify how many quantities I need to specify.
Just one.
Just one. Let's say specify pressure. So once I fix pressure, these two quantities will not change. Let us now go to the phase diagram. I have drawn some isotherms. Okay, I think this would be more appropriate. So figure 3.3, as I go from point B to point B prime at temperature T1, I go from B to B prime, temperature is not changing, temperature is fixed at T1. Pressure is not changing, it's a horizontal line. Pressure is fixed at P sat corresponds to T1. So if I specify temperature, tells you, you will be able to calculate P sat. One relationship we have already seen. Relationship we have seen that gives me the saturation pressure of temperature. Chapter 1, you have seen that equation. Unit change. What was the name of that equation? Antoine's equation. Okay, so that is one relationship that tells you P sat as a function of T. Okay, anyways, what I know is that. Okay, how I calculate that, that is a different question. So as I go from B up to B prime, what is happening to VL sat? Or staying fixed? So as I went from B up to B prime, you can clearly see V is changing. However, VL sat and VV sat are fixed quantities, and the only reason V, which is the combined specific volume, is changing. Number one, it's not a Gibbs phase variable. So thermodynamics is not putting any constraint on V because V is combined specific volume, and in two-phase system, V is not a property of single homogeneous phase. Okay, the Gibbs phase rule doesn't apply to V. So thermodynamics is not putting any constraint on me. Now physically, the reason this V is changing is because saturated liquid is getting converted into saturated vapor. Why this might be happening? Maybe you are adding heat to the system. If you heat a saturated liquid at constant pressure and temperature, that latent heat would be used to convert liquid to vapor. Okay, so that is the reason why to vapor. And while this liquid is getting converted to vapor, the overall specific volume is changing. So if you look at the vessel, this piston will be able to move up because L is getting converted to V. So VL sat is not changing, VB sat is not changing. That is what thermodynamics is putting the constraint on. Thermodynamics is not putting any constraint on this combined specific volume, and therefore it can change. And indeed, we can see physically the reason it is changing is because liquid is converting to vapor. Vapor is less dense than liquid. Therefore, the total volume of the system increases because the mass is not changing. The mass is fixed. The system is becoming less dense. Therefore, total volume is changing. Okay.
Sir, VL sat and V sat will depend on two intensive variables, right?
No. So that's what we just discussed, right? That if you have a pure species at coexistence, pi is equal to 2. Pi is equal to 2 for a pure species.
Sir, but pi is equal to 2 is when liquid and vapor coexist. But we are taking VL sat, which means there is only liquid, but in saturated state,
So
isn't it?
that's a good question. Yes. However, uh, saturated liquid also is a special kind of liquid. What is the meaning of saturated liquid?
Sir, in the PT graph, there were three possibilities in the curve where the
Yeah.
liquid and vapor would coexist.
Yeah. So it is point B, right? Saturated liquid is point B.
Yes, sir.
Okay, and you can clearly see, I mean, we can look at both PV as well as PT diagrams. So in the PV diagram, this curve BCD, I gave the name binodal. This curve is already present, independent of your process. This curve BCD is not dependent on your process. This I can draw a priori, okay? Like here I did on the right also, right? So this curve BCD, known as the binodal, where BC is all saturated liquid states, CD are all vapor states. Okay, so this BCD is available to me already, and saturated liquid is in a way a special kind of liquid phase, verge of transition. That is why we are calling it as saturated liquid. So 100% saturated liquid as well as 100% saturated vapor also being considered as phases at coexistence. Even though physically no vapor or no liquid, that means the second phase is not present. But even then we are considering them at coexistence. And if you go to PT diagram, it will be even more clear. Section point could be B or it could be B prime or it could be anything in between. And you can clearly see here that this curve a priori tell you I have saturated liquid, let's say saturated water at 1 bar. All you will do is a horizontal line at 1 bar, find out where it intersects with this curve 2C. Wherever it intersects with curve 2C, you will be then able to calculate what is the temperature. Similarly, if you go to PV, like we did here, tell you the pressure, you will draw a horizontal line. And from there, you will be able to calculate VL set for the liquid at B. Similarly, the vapor at B prime. Okay, so therefore, for B and B prime, degrees of freedom are 1. Okay, because I'm taking pi equal to 2. So short answer is saturated phase at coexistence, irrespective of whether it has physically the other, it is at coexistence.
Oh, so B and B prime are saturated, but in between BP prime, is there saturation as well? I mean, are they also?
Yes. So I believe this was also mentioned. I'm just trying to look at. Yes, I believe. Yes, right. So this is the correct place. Okay. So what you are seeing here is, I'm saying at B, you have vapor liquid coexistence. And there are 3 possibilities. All of the material is in liquid state at saturation. All of the material is in vapor state at saturation. Or you have a part of the material in vapor phase, part of the material in liquid phase. All 3 are diagram, a single point represented by B. On the PV diagram, it's a line. Okay. The possibilities are either you have saturated liquid. So rather than, I mean, in terms of, you can either count it as 3 possibilities or you can simply state the meaning of vapor liquid coexistence is that you have a saturated vapor with saturated liquid. And now the amount of this vapor, which we are representing by this curved quantity, can be anywhere from 0 to 100%. And the amount of your liquid can be anywhere from 0 to 100% in terms of the volume occupied. If you're doing it in terms of fraction, then it will be 0 to 1. And I believe that's what I have done there, right? I have defined these as fractions. So 100% means this quantity V will be equal to 1. Similarly, 100% of L means quantity L will be equal to 1. and with the constraint that V plus L is equal to 1. Okay, so this covers all possible answers which you will obtain on the PV diagram. Okay, V can lie anywhere between 0 and 1, L can lie anywhere between 0 and 1, as long as the sum of V plus L is equal to 1. Okay, so if you now go to PV diagram, at B, V is equal to 0, L is equal to 1. At B prime, V is equal to 1, L is equal to 0. And in between, L is decreasing from 1 to 0, V is increasing from 0 to 1. But all states for us at coexistence, saturated liquid at volume V sat in equilibrium with the saturated vapor at a specific volume of VB sat. Okay. Does that explain the various states I will see between B to B prime?
Yes, sir. So, sir, saturation only means that the pressure should be Psat of the combined. Is that so?
Yeah, we can say that, yes. That when I'm saying I have a system at saturation or at coexistence, all I'm saying is that what will be the most, actually you can see from here itself. So let's say the temperature is the one I'm controlling here. Temperature is T1. So now the system, I will say that saturation when pressure is equal to Psat. Okay, that's what this PV diagram or PD diagram is showing. That if I'm taking a particular temperature T1, the system will reach saturation. So in this case, I started at point D. I started to decrease pressure when the pressure was equal to Psat. That's when I reached saturation. Okay. Any other questions, queries? All right. So few things which I want you to think about and maybe ask again after you've thought about them. What is the meaning of local thermodynamic equilibrium and how it is implicitly being used in our energy balance equations? I've asked in the lecture, marked for discussion, but no one has asked. But again, just asking is not sufficient. First, think about it. And secondly, how the phase diagrams change as the nature of interactions change. So phase diagram of a few fluids, yourself, CO2, ammonia, values of pressure and temperature, and the shape. Both are important here. So absolute values as well as the shape, they tell you a lot about the nature of intermolecular interactions in these systems. Okay. So these are a few questions which you need to delve on, and then you can ask me tomorrow or whatever in the next discussion session. Chapter 1, any problem which you want me to discuss. So from my side, chapter 1 problem sheet, you should be able to attempt everything. If there is something where you are getting stuck, please let me know. So chapter 2, one specific problem which I will discuss. Let me see the problem number so that 2.20. The reason I'm discussing this is a generic asking you to simplify energy balance Simplify the generalized energy balance for a variety of equations. Okay, and in principle, if you can, if you want, actually, if you want to apply any of these equations, energy balance, mass balance, at any scale, be it a single process, be it the entire plant, you will work your way up equations. So you will apply these balances individual unit operation and then combine those equations to get the overall energy balance, overall mass balance at any scale. Okay, so it doesn't matter at what scale you are working, you will still need to apply the equations at individual unit operations. Okay, so therefore it becomes kind of relevant that we know how to work these equations for given unit operations. Okay, so let us start at the general equation. I am working in terms of mass flow rates, but if there is no reaction in the system, you can as well write everything as it is in terms of it's also. Of course, all the quantities you will need to change. Okay. So for example, 1 half U square Z into G, they are specifically potential energy, kinetic energies in terms of per unit mass. If you define them in terms of per unit moles, some changes will be required. Okay. So this is my starting point. Now let us look at individual operations. So 2.20, the first problem is a single pipe heat exchanger. Let's see how it looks like. So you have a single stream of fluid and you are providing heat by some means. There are no moving parts in the system, so shaft work component is 0. Times you will be able to ignore potential energy change as well as internal energy change. Okay, but again, that will depend on the details. Okay, so you have to typically first calculate and then show this is negligible. Sometimes you'll see indeed it is negligible. All right. As far as problem solving is concerned, many times we'll specify. But if you want to check, all you need to check is what is the magnitude of these quantities. Checking. So compare the magnitude of these quantities with respect to other relevant quantities in the system. In this case, the other relevant quantity is per unit mass, enthalpy change per unit mass. These two is the kinetic energy change and potential energy change per unit mass are much smaller than these other two quantities, delta H and Q naught by M naught. Then you can say that it's okay to ignore them. Okay. And what I'm saying is most of the times that would indeed be the case. Okay, we'll also see case chances when that is not the case. So once you do all this, I assume steady state, in fact, That assumption. So this is not fully general. All of these processes are given to be steady state. So I've already assumed steady state operation. So therefore, that first quantity I have already ignored. Okay. Mass flow rate at inlet would be equal to mass flow rate at outlet because it's a single stream. No splitting is happening. So I place it by a single symbol M naught. So I put all of this in the equation and all I will get is, which probably you would have assumed intuitively, that the increase in enthalpy of the flow stream would be equal to the heat input. That's all we are stating essentially. That the enthalpy is increasing of the flow stream and the amount by which the enthalpy would increase would be equal to the amount of heat input to the system. Second case is a double pipe heat exchanger. All of these problems, it would be best to first draw the schematic of the process and then attempt to do something. Okay, if you can draw the schematic correctly, most likely you will put the correct simplification also. So that is your stream 1. And on the other side, you have your stream 2. Okay, so, and typically all of this thing, so I will draw my control surface. I will draw my control surface in such a fashion that all the flows in and out of the control volume are happening across my control surface. So this red denotes my control surface. Typically, these heat exchangers are insulated. So in this case, Q naught is also 0, no heat exchange with the surroundings. Okay. So in the single pipe case, we are providing heat from outside. In this, typically you will be having a second flow stream, and the main mechanism is of heat between the two flow streams. Okay. So Q naught is 0, no moving parts. W naught is 0. Here, even though there are small height differences, you can see stream 2 especially is entering at the top, exiting at the bottom. But again, you will see most of the times these two quantities are small. So you would be able to ignore them. Okay. So after putting in all the simplifications, so M1 naught is the flow rate of stream 1, delta H1 is the change in enthalpy of stream 1. Similarly, M2 naught, delta H2 naught, which essentially says increase in enthalpy, total enthalpy of stream 1 is equal to decrease in total enthalpy of stream 2, or vice versa, depending on which stream is getting and which stream is losing heat. Okay. So at the end, again, you are getting an intuitive answer, but it's best to do it in a correct way, which is general energy balance. Write down your assumptions quickly. Okay. Now they're asking about a pump with a single liquid stream. So 1 and 2 are your entry and exit points. Again, there's only one stream. You can draw your control surface across the pump, and here whatever work is being supplied to the pump, I'm modeling as coming from outside. So the electric work is being taken as input to the system. So that means W naught in this case is not zero. And the way you can visualize shaft, the way this pump is working is, it's connected to a power source. A shaft inside which is moving, and rotation of that shaft is mechanism by which the electric work is getting added to your flow stream. Therefore, W naught in this case is not zero. Again, 1 and 2, height difference would be very small. So this typically you can ignore, but there is a kind of pump where you cannot ignore this quantity. What kind of pump is that? So for a pump, it's not necessary. You can always ignore this quantity. What are the uses of pumps? Say it again.
Sir, every pump is used for water, I mean, fluid flow, right? Or, I mean,
Yes, but there are broadly two reasons you are using a pump. Those. So yes, you are using it to move a fluid, but even then there are two jobs, different kinds of pumps on a broad basis.
Extraction from ground of groundwater.
Yes, in a way. So one use of a pump, to state it in general, is to transport a fluid to a low level to a high level. So one job of pump is to transport vertically, so to say, right? And what is the other role of a pump? To add kinetic energy, transport it over long distances.
Yes, sir.
Right? So velocity. What is the third? So three actually, right? So number two role I mentioned is, you want to increase the flow velocity. That is the job of my pump. Okay, third. Something what a compressor is doing in a sense. Compressor is also, you can say, it's kind of a pump. Increase the pressure of the flow stream. Okay. So pumps come in various flavors. Either I want to transport vertically, so to a height, or I want to increase flow velocity. That could be my main purpose. Or I want to increase pressure. Okay, so depending on which kind of pump you are dealing with, you will have a different simplification of your generalized energy balance. So here, let's say specifically, I'm looking at this kind of pump. So what is the expectation? Which term would survive in your general energy balance? Let's say you're not doing anything. You just first want to intuitively ask which term would survive for this kind of pump. Which term in your equation is strongly dependent on pressure in the generalized energy balance?
Enthalpy term.
Enthalpy term can change significantly, right? We don't know. For some fluid, it might not. For some, it might change a lot. Okay, so I cannot ignore it a priori. So if my main purpose was to increase the pressure, Flow velocity, I'm assuming, has not changed much. But again, this is something which you cannot ignore directly. So I am just putting the mark, be careful. So it's better to do the calculation, because if the pressure has changed, depending on what kind of fluid you're dealing with, density can change a lot. Okay, if it's a liquid, you might be safe. For a liquid with pressure, density will not change much. If the inlet and outlet pipe diameters are not too different, the change in kinetic energy will be negligible. Okay, but again, that depends on the kind of fluid you're dealing with. Okay. And assuming either the pump is insulated or the temperature is very close to the surrounding temperature, in either case, heat gain or heat loss is also small. Again, all of these are what typically happens. But if you have a special circumstance, problem statement is saying otherwise, you have to account for those special circumstances. Okay. So putting all of this, I get again kind of an expected answer that whatever work I have put, that has gone into increasing the enthalpy of the system, and that is most relevant, or this is going to be applicable for a pump whose main job is to increase pressure. Okay, so maybe as a self exercise, each of these pumps have a name. So depending on the job they are doing, you have a different name for that pump. So put in these blanks. Okay. Let's go to the other two parts.
Sir?
Yes.
So in the double pipe heat exchanger, why have we considered M1 and M2 as constants? I mean, are we saying that the inlet and outlet conditions for the stream 1 is same? Are we saying that because M1 has been taken out of the delta sign, right?
So M1 corresponds to the mass flow rate of stream 1. So if you have steady flow conditions, whatever mass of stream 1 is going in, same would come out.
Okay, sir.
Okay. I'm not saying M1 naught is equal to M2 naught. Okay.
Yes.
Right. So okay, maybe I think that problem has come because of, so here you see we will have two kinds of ones and twos floating around. So if we want to make our life easy, maybe I don't know how much I will be able to follow convention. So let's say the streams we refer by superscripts. Or okay, so let's not do that change here. So this I keep as it is, let's say. And when you're talking about the same flow stream, inlet and outlet, either put I or F or put the index in the bracket. Okay, so maybe that's the, was that the reason for confusion in
Yes,
part
sir.
A,
I thought that
right?
1
I
and 2
understand.
correspond to inlet and outlet. That's why
Yes,
I
yes, I
asked.
understand. I understand. So I agree this can lead to confusion. So, but as long as the context is clear, so here I was clearly specifying one is stream one, two is stream two.
Yes, sir.
Okay. So put in these cases, if you further want to specify inlet outlet, put the inlet outlet index either in a bracket or in a superscript. Okay.
Okay, sir.
Part D and E of this problem. So a gas compressor and a gas turbine. Very different equipment, but in terms of energy balance, very similar to the kind of energy balance I've done for a pump in part C. Okay. So a gas compressor job is again to increase the pressure of the flow stream by input of work from outside in a turbine. It's the reverse process. You have a high pressure stream device. That device has, let's say, blades. That's why we're calling it a turbine. So it impinges on those moving blades. As a result, you get some work output from a turbine, and a low pressure stream exits the turbine. Okay. So the job of a turbine is to obtain work, extract work from a high pressure input stream. Okay. So that is your compressor, and at the bottom is a turbine. The energy balance would, and both of these typically we can take to be insulated or heat loss negligible because of other reasons. Again, the design, the energy balance would be same as C. Okay. Same as part C. Now let us come to the last one, or maybe two, throttle valve, F. So if you take a look at a throttle valve, it is kind of a cylindrical, you can say cork kind of thing with some holes. And the main purpose of a throttle valve is to cool down an inlet stream. Typically, the inlet stream would be coming at high pressure. The exit stream would be at low pressure and low temperature. So main aim of a throttle valve, even though expansion is happening, so it's an expansion device. And the main job of this expansion device is to cool down the inlet stream. Okay, so it is used in refrigeration cycle. So if you want to visualize refrigeration cycle, you already have two components of that. You have a gas compressor, which will take your stream to high pressure. After that, you will put your stream to a throttle valve so that that high pressure stream, after exiting the throttle valve, has cooled down significantly. Once we come to chapter 9, we will actually look at numbers, or even chapter 6, 7, we'll look at numbers to understand, depending on the conditions of the inlet stream, you can get very different amounts of cooling. Okay, anywhere from a few degrees Celsius to hundreds of degrees Celsius of cooling, depending on the inlet conditions. So same fluid, same throttle valve, just changing the inlet conditions, you can get very different degrees of cooling. Okay, and again, you will definitely want to insulate this. Otherwise, is essentially not doing its job. Okay, so if you don't insulate it, then whatever cooling you get, it will be lost to the surroundings. Your steam can get heated again. Okay, so this is insulated, no moving parts. So in some sense, just the design of this equipment is sufficient to provide you cooling. You don't need any moving parts, you don't need any work input. Okay, so somewhat magically, your flow stream will come out as a cool stream. All right, so putting in all this, what you get is delta H equal to 0. This has a special name, isenthalpic process, a process where enthalpy is not changing. The throttle is an isenthalpic process. Q naught is 0, W naught is 0. I am ignoring the potential energy and kinetic energy changes. The only thing which is left is H. Okay, so throttle valve, enthalpy change is 0. Last is a nozzle. What is the job of a nozzle? use nozzles in processes in industrial settings? To increase the velocity. Okay, so typically it will have a very narrow outlet. So which term I cannot ignore, which I've done so far,
Kinetic energy.
right? So in this particular case, change in kinetic energy will not be zero. Again, no moving parts. The nozzle is either insulated, or you can say that typically you will see it is maintained actually not insulated. But even then, the temperature of the flow streams is very close to surrounding temperature. So heat exchange is negligible. The heat exchange with surroundings is still negligible, even though it might not be insulated. Okay. So we'll never write them to be zero because they're not strictly zero. The change in potential energy, again, I am saying would be small in this setting. So put all of these, and again, you get somewhat intuitive answer. That is, it's an interconversion between enthalpy and kinetic energy. So enthalpy of the steam is getting converted into the kinetic energy of the steam. So you need a high enthalpy steam. Again, one easy way to do that would be high pressure at the inlet. Okay. So the enthalpy of the flow stream is getting converted into the velocity of the flow stream. Okay. That is your nozzle operation. Okay. So that in some sense is a pump, but without any work input. A pump which is increasing flow velocity, but without any work input. Okay, but not all requirements of a pump whose job is to increase flow velocity can be satisfied by nozzle, because nozzle there is a constraint. It's only internal conversion. Okay. So only if you modulate the inlet conditions, you can get the increase in flow velocity in a nozzle. But if you want to go beyond that, you will need to use a pump. You will need to add work, and then your answer becomes somewhat independent of the inlet pressure temperature conditions. Okay, you just modulate the work input, and by modulating the work input, you can modulate the exit velocity. So depending on the job, you might use a nozzle or a pump to increase flow velocity. That will all depend on how much velocity increase is required, what are the inlet conditions you are dealing with, and what are the target outlet conditions. So all those questions would lead you to selecting one over the other. So that's all for today's discussion session. Whatever few problems are left, I would advise you to first try to work on your own. This 2.20 in principle allows you to work on all the other open system problems. Okay, all they now include is details of the specific process, but a large variety of unit operations we have already discussed. Okay, and then whatever queries you have, questions you have, challenges you are facing in problem solving, we'll discuss in tomorrow's tutorial. Okay, so I believe 1 to 2 p.m. Is there anyone, because I have not received any email, so is there anyone who for whom 1 to 2 p.m. does not work? So Tuesdays 1 to 2 p.m. can be fixed throughout the session.
Yes, sir.
Yes, sir.
Yes, yes,
Anyone
sir.
with a clash can
Yes, sir.
let me know. Anyone who have a clash, that's maybe the absolute last chance. Okay, so let's fix then 1 to 2 p.m.